Hello friends, let us study high energy ready to eat food paste part 2. In the first part of this lecture, in the last class, we studied general aspects of ready to eat food paste, like what are different ingredients, how the ingredients are formulated, and then what are the different processing steps, maybe primary processing, batch wise processing, or then finally this continuous processing, post processing, packaging and safety, cleaning of the equipment, etc. So, we took an overview or in general process details of in general ready to eat food paste, and those things can be in fact applied with for preparation of such food of any characteristics, any type, or containing any specific micronutrient, any specific composition, that is protein, fat, etc., etc. So, in this second part of this lecture, we will concentrate on formulation, processing, packaging of a high energy ready to eat food paste for severely acute malnourished children. And the most of this work we will be presenting on the basis of our own experimental results. So, first of all, let us see what are the severe acute malnutrition. In the earlier classes also, we little bit deliberated on this when we were discussing iron fortified rice manufacturing or other, that malnutrition is a global problem, global health problem. In fact, about 50% of the child death globally are because of the malnutrition, and among in this severe acute malnutrition is a major problem. It is a cause of the important cause of the morbidity and mortality in the children. You can see in this figure, this child is severely acute. It is basically that is the protein and calorie malnutrition. Body is in deficient supply of energy. So, when there is a deficit supply of energy, then the requirement, then body uses protein for energy purposes, and which ultimately results into the protein deficiency as well. So, overall in nutshell, the body become deficient to protein and energy, it is protein energy malnutrition. Now, normally Kwashiorkor or marasmus, etc., that is it may result into stunting or very less body weight and so on. There are various symptoms. So, in fact, WHO and FAO data says that about 15% of the SAM children worldwide, they might require inpatient management. There may be some, of course, there are also not some medical complications, but some medical attention, doctor attention, they require feeding under the attention or care of some doctors, but remaining 85% can be managed through community based or home based care approach. And the treatment of SAM therefore occupies a unique position between clinical medicine and public health. So, it becomes very important, and of course, once that severe acute malnutrition or the child recovers from, then it may come under the medium acute malnutrition. So, the for recovery for the child suffering from severe acute malnutrition, therapeutic feeding for the management of SAM is needed, whereas the moderate acute malnutrition can be taken care of by supplementary feeding. In the earlier class also I gave you this information. So, the WHO and FAO, they have recommended a specific formulation, that is the food, therapeutic food for the management of SAM children should have the moisture maximum 2.5%, energy 520 to 550 kilocalorie per 100 gram, and then 10 to 12% of the total energy should come from proteins, 45 to 50% of the total energy should come from fats, etc., and similarly the micronutrients, etc. So, in fact, in the preparation of this ready food paste, that is the appropriate raw materials, that is locally available raw materials, peanut paste or such other materials are used, and then they are in the proper proportion decided by the linear programming formulation, and then they are treated, processed and packaged. So, maybe in the next few slides I will tell you that we have how we have gone through the preparation of a ready to eat food paste for the management of severely acute malnourished children. So, we at IIT Kharagpur, using locally produced raw materials, have developed 5 formulations of ready to eat food paste, high energy ready to eat food paste, and these like 3 formulations are of a peanut based, PN1, PN2 and PN3. That is, PN stands for peanut, there the main ingredients is peanut, and supporting ingredients may be skim milk powder, sugar, glucose, soybean oil, or some has the maize flour, or has the soya protein isolate. So, different combinations, and the remaining 2 ingredients, one is the potato based, other is the Bengal gram based. On an average basis, in these materials, that is the milk powder in all these formulations, milk powder on an average it is about 30%, because as I told you in the last class, that is the complementation of the protein, essential amino acid, because the milk children, growing children, newborn, severely acute malnourished, SIM is a major problem. Newborn baby, that is a baby from 6 months to 6 years. So, they should be provided adequate protein, milk protein for their proper development, right. So, the milk powder or milk protein about 30%, it contains peanut butter on an average about 25%, sugar around 28%, vegetable oil 15%, and this vitamin and mineral premix about 2%. So, it is a general composition. I am giving you just indicative range. We have developed this process, it is patented. So, just indicative range I am giving you. So, we have developed a pilot scale manufacturing unit also. So, we will discuss the pilot scale production of this product. So, obviously, that is the I will be discussing one peanut based one formulation, and the same even the peanut based, Bengal gram based also can be done using by the same, and for potato based ingredient, of course, some additional boiling or blanching units might be required. So, we have raw material, 2 group of ingredient, 1 group of ingredient raw material, peanut, maize and soybean, and processed ingredient we are using in our formulation, skimmed milk powder, sugar, vegetable oil, vitamin mineral premix, and some emulsifier and stabilizers. So, this is the process flow chart, this for preparation of those 5 formulations. As I told you that these cereals and pulse grains, food grains like peanut, maize, soybeans, they are subjected to different treatments like cleaning, then dehulling and roasting. So, this cleaned and dehulled maize, etc., they are roasted and cooled. Then this roasted peanuts or all these roasted grains are ground to desired particle size, okay. And sometimes depending upon the type of the grain, sometimes even roasting can be performed before dehulling, or that is the roasting can be done after dehulling, because some grains where this husk is very tightly adhering to the. So, some initial, that is of course, little bit heat treatment, it may facilitate the roasting process, but in general the grains are dehulled and then roasted. So, this roasted peanut paste, roasted maize flour or soybean flour, etc., and the other the potato flour, that is potato is boiled, dried, and this boiled potato flour. So, basically we are having cereal grain flour, oilseed paste, or the Bengal gram flour. So, they are given heat treatment, roasting, etc., to improve their digestibility and other properties, and then they are finally mixed as per the formulation to get the desired product that is mixed with sugar, skim milk, vegetable oil, etc., are mixed. The same process you can see in this flow chart, that is the ingredient wise, that is a ready to eat food paste manufacturing process operations, that is 3 grains you see is peanut, soybean and maize. This is the pass through the roaster, then this peanut is de-skinned, that is the removal of the skin, red color skin. So, you get a roasted peanut splits, and these roasted peanut splits are passed through Herschel mixture to convert it into paste. So, we get peanut butter or peanut paste, right. Then these 2 grains, soybean and maize, they are roasted, and after roasting, there of course, before roasting, cleaning and grading, etc., cleaning, grading and dehulling, splitting, and then roasting. After roasting, they are ground to have a pass through gyrosifter and have a proper particle size flours, and these all the maybe peanut butter, the soybean flour, maize flour, vitamin mineral premix, sugar powder and skim milk powder. So, they are mixed in the Plowshare mixer, and finally, in the colloid mill they are homogenized, or where that is all the particle, it is a second stage milling of fine particles up to colloidal size, maybe 200, less than 200 micron, or even as low as possible, maybe 100 micron or 50 micron, it will be much better. So, this gives also a uniform mixing and provide the paste, makes the paste homogeneous. Then finally, it is set to the packaging machine, and you different size of packaging machine is obtained. So, in this table, just in the for the pilot plant, what the equipment selection, depending upon the raw material, depending upon the process operations, different equipments are selected, and of course, the properties, characteristics of the material, their physical properties, all right, respective physical properties for which is important for the respective operation. Those are considered. For example, for the cleaning of the peanut, maize, soybean, a suitable air screen cleaner cum grinder may be taken, that is which can remove the cleaning, and here physical property like bulk density, moisture, angle of repose, size and shape, geometric diameter, sphericity, capacity of the cleaner to be desired. All these considerations are taken, and accordingly appropriate size or appropriate make of the cleaner is selected. Similarly, for cleaning of the sugar, even gyrosifter may be used, or equipment and the type of the sieve, etc. in the gyrosifter which is to be, then maybe bulk density, particle size or capacity, etc. agar considerations or selection criteria. For roasting of the peanut, maize, other grains, that is the suitable roaster, the roaster type and size should be decided on the basis of the bulk density, initial and final moisture content, temperature and so on. Similarly, for the different, because after the roasting, before grinding, sometimes the seeds might be required to be prompt cooling. Otherwise, if the cooling is not done efficiently, or cooling is not done immediately, then the grain may be higher temperature for longer time, and which may cause some change in the composition. So, the dry cooling unit, then again terminal velocity, hardness, size and shape, angle of repose, etc. are the criteria for the selection of the cooling unit. For the then the grinding, it may be burr mill, or it may be other similar mill, artisan mill, etc. can be used, and the capacity and moisture content of the grain, roasted grains, etc. and the particle size, required particle size are the important criteria for the selection. Similarly, for the roasted soya flour and roasted maize flour, there is screening in order to get these material of proper size gyro shifter is may be used, and the capacity of the gyro capacity, how much we want to say, what is the bulk density of these material, their particle size required. These are some of the criteria for the selection of gyro shifter. And then for the split peanut, roasted peanuts, this grinding and mixing is the unit operation. For this Hensel mixer is used, and the Hensel mixer for the selection of the capacity or size of the Hensel mixer, particle size, what is the amount of the split peanuts to be ground or make it into paste, or viscosity, particle size, all these are the important selection criteria. Then I will now, with especially for those who are in our pilot scale unit, these are the equipment pictures I am showing. With this we have a roaster, developed roaster, which is gives that thermostatically controlled and dry heating. We have the arrangement here where the temperature and time etc. properly can be maintained, and even the temperature inside the grain, inside the roaster, the grain temperature can be measured using the thermocouples or sensors. So, the grains are passed into this for the desired time and temperature, and they are roasted. So, obviously, as I told you earlier also, roasting improves color, texture, enhances flavor, and improves the digestibility of this. So, in this figure you can say it is a based on our result, and we have published it. There is the browning index and protein digestibility of the material, how the roasting time and temperature influences. Similarly, we have done in the case of maize, in the case of Bengal gram also, in the case of soybean also we have studied, but here I am just reporting the maize. The equipment used was, as I showed you in the last slide, the picture roaster, designed and developed and got fabricated by us. Then experimental design uses the CCRD, and independent parameters were that roasting time from ranging from 10 to 35 minutes, and temperature of the roasting was 170 to 200 range. So, you can see here that both the protein digestibility as well as browning index, they varied significantly. That is the time of roasting, temperature of roasting, they had significant effect, and even the roasting time and temperature combination, they had significant effect on the protein digestibility and browning index. In fact, in the maize, the protein digestibility increased from initial 59 to 60% level to finally 87 to 90%. So, the protein digestibility was significantly improved, drastically improved. Even the color index also you can see here, that is browning index was increased. So, material. In this, these are the scanning electron microscope SEM images of raw and optimally roasted maize samples, right. That is even A, this is the raw and this is the roasted 750x, 1500x and 3000x magnification levels. So, you can see in the picture it clearly shows that raw maize flour had more compact and tightly packed and smooth structure, whereas in the roasted sample the starch granules were largely deformed, they were swollen and became fragmented along with structural collapse, but of course, they were well distinguishable. So, this clearly says that is the roasting causes the structural change into the material. Then after the roasting, that is de-skinning is an important operation for the roasted peanuts. That is our roaster, we have another unit attached with it, that de-skinning, it is basically a drum cooling unit. Okay. This drum cooling unit consists of a rotary cylinder provided with baffles inside. It cools the warm peanut with counter current airflow, that is the peanuts is fed from here and the low temperature that is peanut is fed from this side, and low temperature air comes from the other opposite direction. So, while the peanut moves here, this drum rotates. So, there is a efficient heat transfer takes place, and the peanuts get cool down, and then once that temperature is cooled down, brought down, then it also loosens the adherence between the peanut meat, that is the split, as well as skin. So, this in the next, in the de-skinning, the removal, that is the de-skinner, that is the cooling unit is attached with a de-skinning unit, where it is there they are provided with that every that is the roller which removes skin and splits the peanuts. So, the roasted peanuts, finally, they are got de-skinned peanut splits, right. So, it is provided with a cyclone separator which removes the skins. In this figure, you can see that both the speed of the drum of the decooling unit and the temperature of the air or temperature of the material, they have the important influence on the cooling time. That is the effect of the temperature drop in the inside the drum. See, that is this is the upper line, red lines, they have the material fed at 82.6 kilogram per hour, and the bottom line has the material feed rate is the 96.6 kilogram per hour. So, both the feed rate of the material peanuts in the cooling unit, the temperature of the cooling unit air, and that is it speed of the, they have the important influence in the temperature draft, that is the dt, delta T. Then after this, the material is ground. So, grinding of the cereals is normally done, as I told you, in the Atchison mill or hammer mill, they are used for the proper grinding, and high speed and feed rates produce more fine particles as compared to the lower peripheral speed and feed rate. So, the feed rate as well as peripheral speed has important influence. The particle size of the floor greatly influences the water absorption as well as oil absorption, and also the flowability of the floor. So, the floors are finally, after grinding, they are shifted in gyro shifter to maintain the uniform particle size. This is the picture. This you see that here is the for the ground nut, that peanut plus oil plus stabilizer, mixture of that in the required formulation as decided by linear programming, they are put here, and then this is the vegetable oil tank, the stabilizer, and dry ingredients, they are put into these various containers. This is all primary, that batch wise, sorry, this is a, this section is your continuous processing and packaging. So, I will show you in the actual machinery also, pilot plant photographs. This earlier also I explained. So, the peanuts and oil and stabilizer and antioxidant, they are converted into fine paste. The paste is obtained here, and then all the dry ingredient like soybean flour, roasted soybean flour, roasted maize flour, then sugar powder, vitamin mineral premix, they are all as per the formulation, they are collected here in this. So, in the secondary stage, they are put to this mixture, where this paste as well as solid powders ingredient, they are mixed, and then finally, they are passed through colloidal mill. So, this picture shows that this is the picture of the Hensel mixer, which is used for peanut grinding cum mixing, and this figure response surface graphs shows the effect of this time, temperature as well as batch size, time and batch size, and the viscosity of the peanut paste produced, as well as particle size, that is particle size yield in the % particle size is of the peanut paste. Okay. And this both time of grinding as well as size of the material used in the grinder, size of the batch, they have had a significant effect or influence. Time, the blend of the peanut, refined oil and food additives after grinding come mixing has a smooth granular particle. Then homogenizer, this is the picture of the actual our pilot scale unit. The material comes, it is a colloidal mill where the gaps are properly adjusted in order to give the desired size, particle size. So, finally, after the colloidal mill we get a homogenized paste material for uniformly mixed material. Okay. So, in this basically this colloid mill reduces the solids which are present in the suspension or emulsion, or the reduction in the suspension droplet size may be there. So, ultimately, because maybe that depending upon the conditions, some powder, the peanut paste also may have a little more higher consistency, the powder sizes may be vary, but this finally when they are mixed together, or there may be some lump formation in the mixing. So, in the colloid milling, this all they are smoothened. The particle size of the peanut paste is reduced as much as possible, maybe less than 200 micron. In fact, in our pilot scale unit we can go up to 150 or even 50 micron, 150 micron. The energy consumption increases as the recirculation time increases, which is indicative of reduction in the particle size, the homogenization in the colloidal mill. So, energy consumption increases as the recirculation time increases. This you can see, this is the picture. So, the recirculation time and then viscosity of the paste and energy consumption, okay, and this paste particle yield. So, this squares these lines, this shows the energy consumption, this your triangle points, they show the paste particle yield, and the circular points, round points, they show the viscosity. So, you can see here both the recirculation time, right, and this they have the important effect, has important effect influence, because this grind and it is recirculated, right. So, for how long it should be recirculated in the Hensel mixture, that it has important influence on this. So, from this side you can see that around a recirculation of about 20 minutes gives, because after 20 minutes there is almost this paste particle yield is becomes straight line. So, there is not much, right. Also this viscosity, but the energy consumption is increasing, going more increasing. So, it may be that is the recirculation time of 20-25 minutes might be desirable, better. After that, the next step is the mixing. In the Plowshare mixture, you can see this is the picture. So, this as I showed you in the earlier flow diagram, there are two streams, feed 1 and feed 2. Feed 1 is the paste and feed 2 is the powder. It is basically that is the solid and liquid mixing, liquid or solid and paste mixing together. So, in the feed 1 roasted peanut paste containing vegetable oil, emulsifier and stabilizers there, and in the feed 2 is the roasted maize, soya flour, sugar powder, skim milk powder, vitamin and mineral premix blend. So, blend up all this as per the formulation, and these two are now mixed in the Plowshare mixture. So, it is basically to make sure that all the ingredients again are properly mixed. It provides 3-dimensional movement of the product, and it results into better mixing or homogeneous mixing of the materials with varying densities, particle size, flow properties and structures. They are carried in less time with almost 95 to 98% homogeneity is obtained in a few minutes. Then this shows that optical microscopic images showing the homogeneity of the ready to eat food paste produced in our pilot plant, and you can see that the oil particles were spread on the surface of the solid particles during the initial stages, maybe before 20 minutes or less. So, later on at the time of mixing increases, that as you can see here, after 30 minutes the sample obtained after 30 minutes, that is here solid particles were surrounded with oil globules and a network formation occurred after finally after 40 minutes of mixing network formation occurred. So, this was a water in oil emulsion formed, which is inverted emulsion. These are due to the, because it is a water in oil emulsion, because water content is comparatively very low, that is less than 2.5%. These are some of the 5 formulations, these 3 peanut paste samples and potato based sample and Bengal gram based sample prepared in our in our pilot scale unit. Finally, packaging, this is the form, fill and seal machine which is used for the packaging of the sachets, and in these packaging machines packets of starting from 50 gram to 100 gram or even more, having appropriate size and packaging machines. So, the appropriate size package sachets can be obtained. We are using LDP with metallic foil sheet for packing of the prepared ready to eat food paste into sizes of 50 gram and 100 gram. And then sealing, obviously there is the packaging machine should be able to provide effective sealing. As I told you in the earlier class also, proper sealing of the package is very important, and temperature of the sealing has an important effect on the seal strength, that is the seal should have sufficient strength, it should not break during storage or handling. Okay. So, you can see here in the vertical sealing as well as in the horizontal sealing, that is the sealing temperature has important, as the almost as around 117 to 120 degree Celsius temperature it gives, that is the seal strength of about 28-29 Newton per square millimeter. Okay. Whereas, in the case of vertical sealing 112 degree Celsius temperature again can gives about, that is 20-25 Newton per millimeter square. So, the temperature of sealing temperature is a very important factor which should be controlled to get the desired seal strength. Our storage and shelf life, we had conducted storage studies, result of our storage studies, that is the packets which were stored under accelerated conditions at 40 degree Celsius temperature and 90% relative humidity. In our experimental results, we could get 4 months shelf life, right. There was no oil suppression, and according to the standard kinetic models available in the literature, a product with a shelf life of 4 months can be 4 months under accelerated storage, can be stored for more than 15 months under ambient conditions. So, that is, these are the pictures of the packets produced in our pilot scale unit. This is the design in layout of the ready to eat food pilot scale unit. It has a GMP interior design, good manufacturing practices interior design. These are the primary processing section, continuous processing section. From the primary processing section is provided with some entry pass box which is a UV facility, so that all the ingredients which are entering the main plant, they are sterilized or surface treated, so as to avoid any contamination. So, because finally this product is to be ready to eat and it has to be consumed directly. So, it should be made that it should be ensured that it is any contamination free. Then also the persons, those who are entering in the pilot plant, here it is a change room facility is provided. So, they change themselves, then air curtain and air showers are there, air lock and air shower. So, the person enter through air shower, means there is here in the primary actual processing facility, there is no contamination whether from the materials and human personnel, those who are working here in that, they are all contamination free, and even the environment, that is the processing hall is provided with AHU, air handling units, etc. So, that always positive pressure is maintained. So, the material is processed here and then it is automatically sent to the packaging line. And also in the our pilot plant we have some that laboratory facilities. So, to conduct samples are taken intermittently, they are sent to the laboratory for this testing. So, laboratory for testing, the material is entering here, all the material processes, wastes are disposed, and then finally, the finished good. There is finished good storage and the processed material out. So, this is a GMP interior design for the pilot scale facility. So, pilot plant equipment, there is construction material, normally SS 316 and SS 304. Equipment should be properly sited in appropriate location for easy dismantling and cleaning of integral parts. All equipment section is based on minimization of any risk of microbiological contamination, including the possibilities of inaccessible areas for cleaning and accumulation of residual materials. So, every possible, as I told you that inside the main processing hall, that is a contamination free or microorganism free environment is maintained. So, the surface of the equipment should be smooth, seamless, scratch free and the safely accessible for cleaning and visual examination. The GMP compliance means that is the plant is provided, it should be provided for any plant which is GMP compliant. It should be provided for natural light as well as luminous flux as per the GMP GHP norms. There should not be any chance of any cross contamination between the raw material and finished product. The material handling should be regulated in such a way. Similarly, there should be separate rooms for primary and secondary packaging of the finished ingredients. This HAV system, that is heating, ventilation and air conditioning system should be provided to maintain proper conditions in the packaging room, in the processing room, main processing room. There should be provided a provision for a change room, washing station, air circulation, air shower, dehumidification facility for raw material and finished good storage, laboratory for chemical and microbiological analysis. So, these are the GMP compliance of the pilot plant. So, this is our actual photograph of our pilot scale unit. You can see this is the primary processing where we are roasting the grains as well as peanut and then converting them into the powder of different sizes. That is it is not shown here. On the other side we have a that is a grinding unit. These are the gyro shifters and this is the roaster. As I explained you earlier, that is a drum roaster and material is fed through here and through thermocouples we can this rotates and this is the electrical energy is used for heating the grain inside, and once it is roasted, this is the cooling unit is provided here. It is sent to the put through the cooling unit and then finally cool down or de-escalate. So, it is, and here it is these all the materials, even sugar may be grind here or vitamin mineral. So, all the material passes through this through some trolley, it is passed through. There is a UV facility in, so it goes to the main processing room. Now, here it is the actual main processing room where you can see I showed you in the schematic. These are the actual thing, that is where the solid materials are kept and this liquid, that is your peanut etc. on the other sides they are kept. That is this unit, it is the peanut, oil and this stabilizer antioxidant is kept here. So, this is ground here and paste collected, paste is collected here, this is recirculated and paste is finally collected in this tank. Then and other material from the top solid material, they come and they are collected here. In the secondary stage, that is they are sent to the paste and these solids. This is the other mixer, that is plowshare mixer is put here, and then final plowshare, after plowshare mixer comes to the packaging in the colloidal mill, and through the with the help of pipelines, that is after it is sent to the packaging section. In the packaging section, this is the packaging machine where these different sachets are produced, and these sachets are passed through this metal detection unit and sent for the batch coding. This pilot plant facility is provided with the GMP, equipped with the CIP unit, that is there are, as you can see here, these are the two tanks, two other tanks are there which are not shown in this photograph. So, in one has hot water, another is the hot acid, another has the hot alkali, and then fourth one has hot sanitizer solutions. So, as soon as the material, process material after mixing, plowshare mixing, colloid milling, it is sent to the packaging unit. This automatically this hot water cleaning followed by rinsing, then hot alkali cleaning followed by hot water rinsing, then acid cleaning followed by hot water, finally sanitization, and then dry air cleaning, etc. So, all these things done. This is the same bigger view, same view of the primary, that is the batch PLC control continuous processing unit. So, this is a, here you can see the PLC. In fact, through this, once we set that program, so after that it is a automatic process, that is the mixing, grinding, mixing, homogenizing, conveying and packaging, all this is the automatic process, PLT control process. And even through the software is made in such a way that if there is any particular machine in the whole is some problem, it will indicate, software can indicate the problem, and remedial corrective measures can be taken. So, with this I thank you very much for your patience hearing, and I think you have got in these two lectures, in the part 1 and part 2, quite a good idea of the preparation, that is the formulation, processing and packaging of any ready to eat food paste, as well as the formulation, processing and packaging of specific high energy ready to eat food paste for malnourished children. And these food paste, high energy ready to eat food pastes, which are produced using locally available raw materials, if systematic approach is taken for their hygienic manufacture and providing or manufacture and distribution through proper channels to the affected children and other affected people, and if their feeding is done by proper feeding mechanism, they are provided with these materials, obviously I am sure that this will go a long way, or this will help in eliminating or eradicating the problem of severe acute malnutrition from the nations. Thank you very much.